Your depth gauge surges past 11,000 meters. The pressure enveloping your vessel has now surpassed 1,000 bars. That's over 16,000 pounds per square inch, crushing every single surface. Your radio crackles with a final burst of static, then falls silent. The GPS signal is gone. Even light itself has surrendered to the colossal weight of the water column above you. You have arrived at Challenger Deep, the most profound abyss known to humankind. And here lies the truly unsettling truth. For all our advanced technology, for all our rovers on Mars and our telescopes peering at the edge of the universe, only a handful of humans have ever laid eyes on this place. We have sent more people to walk on the moon than we have to the bottom of our own planet's oceans. Before we venture further into this darkness, I invite you to hit that subscribe button. Let me know in the comments where you're joining us from. Tonight, your support is what fuels our exploration of Earth's most compelling mysteries. What lurks down there, just beyond our reach? What secrets are hidden past the absolute limits of human engineering? And why, after decades of relentless technological progress, do the deepest corners of our world continue to defeat us? The answers may prove more disturbing than the abyss itself. The layers of the abyss, the ocean does not simply get deeper, it transforms. With each layer you descend, another piece of the familiar world is stripped away until you arrive in a realm that might as well be on an alien planet. At the surface, in the epipelagic zone, sunlight filters down to 200 meters. Photosynthesis is still possible here. Marine flora can survive and life thrives in ways we recognize. But the moment you cross that 200-meter threshold, everything changes. Welcome to the twilight zone. The mesopelagic stretches from 200 down to 1,000 meters. Sunlight quickly fades to an eternal dusk, making photosynthesis impossible. Yet, life persists in ways that seem to defy logic. Bioluminescent creatures orchestrate their own light shows in the perpetual twilight. Jellyfish pulse with eerie electric blues, and deep-sea fish flash like living constellations. This is where the ocean first reveals that it operates by an entirely different set of rules. Descend another 1,000 meters, and you enter the bathypelagic, the midnight zone. No sunlight has graced these waters for millions of years. The temperature hovers just above freezing, and the currents move with a geological slowness. It is here that the pressure begins its relentless assault. At 4,000 meters down, you are experiencing forces that would crumple most surface vessels like aluminum cans. But we are still not at the bottom. We are not even close. The abyssal zone extends from 4,000 to 6,000 meters. Here, vast, featureless underwater plains stretch across seafloor distances greater than entire continents. The water temperature stabilizes near freezing. Life becomes sparse, alien, and strange. Yet, even in this seemingly barren wasteland, we have not reached the ocean's deepest secrets. Beyond 6,000 meters lies the Hadal Zone, named after Hades, the Greek underworld. This is not the vast plain of the abyssal. The Hadal Zone is fragmented, a patchwork of profound trenches and troughs carved by unimaginable geological violence. These trenches cover an area roughly half the size of Australia, but represent less than 1% of the total sea floor. They are rare, isolated, and utterly alien. Each trench forms where tectonic plates collide with such force that they tear the seafloor asunder. These subduction zones create immense scars in the Earth's crust, plunging from 6 to 11 kilometers down into crushing blackness. Scientists call it aqua incognita, unknown waters. This is not poetic license. It is a statement of literal truth. The challenge of measurement, a moving target. The deepest of these scars is found in the western Pacific. Challenger Deep, nestled within the southern Mariana Trench, currently holds the record. The most modern pressure-derived measurements place its depth at 10,935 meters below mean sea level, with an impressively small margin of error of just 6 meters. That precision, achieved through 220 submersible transects, relies on gravity and water level corrections that were impossible just a few decades ago. But this is where things get strange. Different studies consistently report different depths for Challenger Deep. The numbers fluctuate depending on the methodology: sonar versus pressure readings, sound speed profiles, geo-wide corrections, even the tidal state at the time of measurement. The 2021 pressure study noted that gravity correction alone can shift a measurement by a substantial amount. The deepest point on Earth keeps moving on our maps. The trench itself is a labyrinth. 3 distinct basins, western, central, and eastern, run along its axis, each plunging below 10,150 meters. They are separated by underwater ridges only a few hundred meters higher, creating a maze of narrow slots and precipitous walls. The deepest section is roughly 11 kilometers long and just over 2 kilometers wide. To put that in perspective, trying to pinpoint the absolute bottom is like trying to hit a target the size of a small city from space. 2 primary methods dominate deep ocean measurement, and each is locked in a battle with the laws of nature. Surface ships employ multi-beam echo sounders, sophisticated sonar systems that send out fans of acoustic beams. The concept appears simple. Sound travels down, bounces back, and the travel time reveals the depth. But 11 kilometers down, sound does not travel in a straight line. Water temperature changes with depth, salinity shifts, and pressure increases. Each layer bends the sound waves, much like a lens refracts light. These thermoclines create what oceanographers call smile and frown artifacts, systematic errors that can make the seafloor appear deeper or shallower than it truly is. Submersibles use a different tactic. They carry high-accuracy pressure sensors to the seafloor and apply hydrostatic principles to calculate depth. Pressure equals the weight of the water above, so measuring pressure should directly reveal depth. However, converting that pressure, reading into a geometric depth requires knowing the exact density of every water layer encountered during the dive. Temperature and salinity both affect density. Then there's gravity. The Earth's gravitational field isn't uniform. Ocean trenches sit within strong gravity anomalies where the seafloor has been pulled deep into the planet. To convert pressure to depth accurately, one must know the precise local gravitational acceleration. Using the wrong gravity model can shift your depth calculation by meters. Reference surfaces further complicate everything. Depth relative to what? The ocean surface is in constant motion due to tides, waves, and atmospheric pressure. The geoid, our best model of mean sea level, requires complex calculations to determine its local height. Choosing a different reference can alter depth measurements by several meters. The numbers shift not because the seafloor is moving dramatically, but because our understanding improves incrementally. The 10,135 meters represents our best current estimate, derived from pressure reference submersible transects with full gravity and geo-wide corrections applied to mean sea level. The +6 meters is an honest admission of uncertainty in a measurement that pushes both technology and physics to their absolute limits. The ocean's deepest number isn't imprecise because we lack skill. It's imprecise because measuring the bottom of the world remains one of the most formidable problems in geophysics. The tyranny of pressure. Engineering for survival 11. Kilometers of water bears down with an incomprehensible force. The general rule is that pressure increases by roughly 1 atmosphere for every 10 meters of descent. At Challenger Deep's 10,135-meter floor, this creates a pressure of approximately 1,100 bar, over 16,000 pounds per square inch pressing against every surface. To put that in perspective, every square inch of a deep-sea vehicle experiences the weight of a small car pushing inward, constantly from every direction. The implosion energy stored in that pressure differential could power a small city for several minutes. When things fail at these depths, they don't simply break, they cease to exist. The research vessel Nereus learned this lesson in the most brutal way possible. In 2014, while exploring near 10,000 meters, something went catastrophically wrong. Recovery crews found only scattered debris fragments. The analysis confirmed a pressure-induced implosion. At these depths, catastrophic failure happens faster than human perception. External pressure attacks materials in ways that surface engineers rarely encounter. Steel and titanium don't just yield as they would under tension. They buckle. Spherical and cylindrical shells develop localized dents that can grow exponentially. What begins as a microscopic imperfection can become a catastrophic collapse zone in milliseconds. For this reason, A hull's geometry is more critical than its material strength. Spheres are superior to cylinders due to simple physics. A sphere distributes membrane stress uniformly across its entire surface. For an equal material thickness, a sphere possesses roughly twice the strength of a cylinder under external pressure. Titanium spheres are the current gold standard for crewed deep ocean exploration. The limiting factor. Submersible, for example, utilizes a thick titanium alloy sphere certified for repeated dives to 11,000 meters. Its machining tolerances approach 99.9% circularity, because even tiny out-of-roundness errors can slash its pressure capacity. Buoyancy systems also face their own depth limitations. Syntactic foam, a composite of resin mixed with hollow glass microspheres, works reliably to about 6,000 meters. Beyond that, the microspheres begin to crush, causing the buoyancy to drop permanently as the foam densifies under pressure. Full ocean depth systems have to abandon foam entirely, using glass and ceramic spheres as solid buoyancy elements that maintain their volume under crushing force. Penetrations remain the ultimate enemy of deep ocean design. Every hatch, viewport, and electrical feed-through creates a potential stress concentration and a pathway for seals to fail. At a depth of 11 kilometers, the ocean relentlessly tests every engineering assumption. Small defects escalate into catastrophic problems. Success demands abandoning surface world intuitions and embracing the harsh reality that deep ocean engineering operates by an entirely different set of rules. The Great Underwater Silence. Communication and navigation. Water swallows radio waves, just as a black hole swallows light. GPS signals can penetrate seawater for mere centimeters before they die completely. The entire electromagnetic spectrum that connects our surface world becomes utterly useless underwater. Submarines and deep-sea vehicles must abandon everything we take for granted about instant communication and switch to acoustic links. Sound. Waves propagating through the ocean itself, but sound travels at a mere 500 meters per second through water. From the floor of Challenger Deep to a surface ship waiting 11 kilometers above, a single acoustic ping takes over 7 seconds to make its round trip. Real-time conversation is impossible. Every exchange is an exercise in patience measured on geological timescales. The data rates paint a sobering picture. Advanced underwater acoustic communication systems support payload rates between 300 and 5,000 bits per second. That is slower than the dial-up internet of the 1990s. Sound doesn't travel in straight lines. Through the ocean, layers of water with different temperatures and salinities bend acoustic waves, just as atmospheric mirages bend light. Shadow zones form where refraction bends sound rays away from receivers, meaning a submersible in a perfect line of sight to its surface ship might still be in an acoustic dead zone. The walls of a trench amplify these issues exponentially, creating multipath propagation where signals bounce off underwater cliffs, arriving at receivers multiple times with different delays. Data packets collide with their own echoes. Ultra-short baseline, USBL, navigation systems offer the best underwater positioning available, but they contend with the same physics. USBL works by measuring the range and bearing from a surface vessel to a subsea transponder. However, geometry betrays precision at extreme depths. The mathematical relationship between baseline length and angular accuracy means that very long slant ranges combined with relatively small surface arrays create large positional errors. A few meters of uncertainty at the surface can translate to tens of meters of uncertainty at the seafloor. The result is a systematic communication breakdown at full ocean depth. Mission planners don't just expect silence, they design their operations around it. At 11 kilometers down, communication is conducted in chirps, not conversations. Navigation becomes a series of estimates punctuated by occasional pings, not the continuous tracking of GPS. The electromagnetic tether that binds our surface world is severed completely underwater. The loneliest club on Earth. Human exploration on January 23, 1960, Navy Lieutenant Don Walsh and Swiss oceanographer Jacques Picard climbed into the Trieste, a massive bathyscaphe buoyant with gasoline and weighted with iron pellets. They descended through crushing darkness for nearly 5 hours until they touched the deepest known point on Earth. 2 men became the first humans to witness Challenger Deep firsthand. And then, there was silence. 52 years of silence. In March 2012, filmmaker James Cameron made the next solo descent in the deep-sea Challenger, reaching a depth of approximately 10,908 meters. The gap between crewed visits to the deepest place on our planet spanned longer than the entire space age. From 2019 onwards, repeatable Hadal diving finally became a reality. The DSV limiting factor commenced systematic full ocean depth operations, completing dozens of dives into the Hadal zone. Multiple visits to different basins within Challenger Deep proved that deep ocean exploration could become routine rather than a heroic once-in-a-lifetime stunt. In 2020, China's Fenduji submersible joined this exclusive club, carrying 3 crew members to approximately 10,909 meters in a titanium sphere engineered for repeated operations, yet the numbers remain staggeringly small. Credible public tallies show that as of 2022, approximately 27 people had visited Challenger Deep. The entire club of humans who have witnessed the deepest place on Earth could fit comfortably in a single classroom. Compare that to space travel. By the mid-2020s, over 600 people will have crossed into space. The scarcity of deep ocean visitors is not an accident. It is a reflection of fundamental barriers. Certified full ocean depth submarines are exceedingly rare. Ship time costs astronomical sums and is difficult to secure. Weather windows can close without warning. International permits create bureaucratic nightmares. It is, in many ways, easier to send a tourist to space than a scientist to the Hadal floor. The Titan tragedy. A cautionary tale. When you are constructing something that will face pressures capable of crushing a car like a soda can, the distinction between it should work and it will work becomes a matter of life and death. Material fatigue is the slow, invisible killer that emerges when materials are stressed repeatedly. Every single dive cycle puts immense strain on every bolt, every weld, and every seal. This is precisely why legitimate deep-sea operations adhere to inspection regimes that would make airline mechanics look casual. These are not mere suggestions. They are the difference between returning to the surface and becoming another cautionary tale. Then came June 2023, and everything changed. The Titan submersible imploded at just 3,800 meters down, a depth not even close to the Hadal zone. 5 people died instantly when their pressure vessel failed catastrophically. The vessel had not been certified as seaworthy by any regulatory agency or third-party organization. This was a deliberate choice to bypass the safety systems that every legitimate deep-sea operation considers non-negotiable. The subsequent Coast Guard investigation painted a picture that should terrify anyone who believes shortcuts are acceptable. OceanGate had consistently sidestepped safety concerns in a push to maximize profits, with its operational and safety practices described as critically flawed. The implosion reset public perception of submersible safety because it demonstrated that even at relatively shallow depths by deep ocean standards, the margin for error is absolute zero. This was not an incident of pushing the boundaries of human knowledge. It was a failure to follow established safety protocols for well-understood operations. The price of discovery, the staggering cost money, descends into the deep ocean even faster than submersibles. The Woods Hole. Oceanographic Institution estimates that the operating cost for Alvin dives, including support from the research vessel Atlantis, runs about $45,000 per day, and that's for reaching 6,500 meters, a depth that still falls far short of full ocean depth. Hadal operations are significantly more expensive. Storms can trap costly research vessels on station for weeks, while daily charges continue to accumulate. The full technology stack required for deep work creates a cascade of costs. The Triton 36002 limiting factor carries DNV classification for repeatable dives to 11,000 meters. That classification imposes design reviews, materials traceability, proof testing, and inspection regimes that multiply both development time and cost. Limiting factor's crew sphere is made from approximately 90 mm thick titanium alloy, requiring precision forging and extremely tight roundness tolerances. Only a few vendors in the world can manufacture pressure hulls to these specifications at any price. Capital costs reach staggering scales. Public reports place the construction cost of the limiting factor submersible alone at around $37 million. The complete Hadal exploration system, including the ship, submersible, and landers, was marketed as a $50 million package. Failure costs multiply catastrophically. Woods Hole's hybrid remotely operated vehicle Nereus, built for approximately $8 million, suffered a pressure-induced implosion at 900 meters in 2014. Japan's Kaiko provided another expensive lesson in 2003 when its secondary cable snapped, causing the entire vehicle to vanish. The budget shock rivals the pressure shock. Deep ocean exploration doesn't just push the boundaries of engineering. It pushes the boundaries of institutional funding to breaking points that few research programs can possibly sustain. Charting the void. The mapping gap A's of World Hydrography Day in June 2025, a mere 27.3% of the global seafloor has been mapped to modern standards using ship-based sonar. The remaining 72.7% of our understanding relies on satellite-derived gravity maps and sparse depth soundings, a patchwork of data that can miss entire mountain ranges hidden beneath the waves. The fundamental resolution problem becomes stark at full ocean depth. Only low-frequency sonar systems can penetrate 11,000 meters of water. At that depth, a 1-degree sonar beam spreads out to cover a footprint roughly 190 meters across on the seafloor directly beneath the ship. Small features, like the narrow slots and micro-depressions that might harbor the true deepest points, simply vanish into these massive acoustic footprints. The consequences of this gap play out in expensive dive time lost to basic navigation. Coarse bathymetric data can place a pre-dive deepest spot hundreds of meters away from its actual location. As a result, initial dives often become search transects instead of productive science operations. The irony is profound. We possess detailed, high-resolution maps of Mars, Venus, and the lunar surface, all created by orbital reconnaissance missions. Yet the deepest places on our own planet remain poorly charted territories where expensive scientific expeditions must begin, with the basic question of where to point their cameras. The seafloor mapping gap isn't just a sign of incomplete knowledge. It actively wastes the scarce resources that deep ocean science desperately needs for advancement. The Symphony of the Deep, a surprisingly noisy world. In July 2015, the U.S. Coast Guard cutter Sequoia deployed a hydrophone mooring into Challenger, deep to record ambient sound. Scientists expected to discover one of the quietest places on the planet. The recordings told a completely different story. The deepest point on Earth buzzes with constant noise. Earthquakes dominate the soundscape, creating a continuous background of seismic rumbling that propagates through solid rock. The distinct moans of baleen whales penetrate 11 kilometers of water column to reach the deepest ocean floor. Human noise reaches even these remote depths. The hydrophone detected the sound of ship propellers and active sonar signals from thousands of miles away. A Category 4 typhoon that passed overhead registered clearly in the recordings, as the storm waves generated powerful low-frequency pressure. Waves. The irony cuts to the very heart of the challenges in deep ocean exploration. The seafloor hears everything. Yet our own efforts to establish reliable two-way communication with instruments at these depths struggle against the same acoustic environment that so efficiently carries natural and anthropogenic sounds to the deepest places on Earth. Sound travels, but data does not travel easily. Life at the limit, biology in the trenches. Life reaches extraordinary depths, but eventually, physics wins. In 2023, researchers filmed a pseudoliparous snailfish at 8,136 meters in the Izu-Ogasawara Trench, the deepest verified sighting of any vertebrate. No fish has ever been found deeper than roughly 8,400 meters. The reason is rooted in cellular chemistry. Fish pack their cells with trimethylamine N-oxide, TMAO, an osmolyte that stabilizes proteins against crushing pressure. Mathematical models predict that around 8,200 meters, fish reach an isosmotic parity with seawater. Beyond that depth, cellular water balance fails catastrophically. But vertebrates represent only a small branch of Hadal life. Microbes thrive in the deepest trenches, and many are piezophiles, meaning they actually prefer extreme pressure. Amphipods, small, crustacean scavengers dominate the visible fauna, yet these seemingly pristine remote environments bear disturbing evidence of surface contamination. Studies conducted across 6 separate trenches found microplastics and synthetic fibers in over 70% of the scavenging amphipods. At the very bottom of the world, our synthetic materials have become part of the food chain. Hadal ecosystems operate on cycles of boom and bust. Long periods of famine are interrupted by massive influxes of resources. Carcass falls from marine mammals, sediment gravity flows, and debris from tectonic disturbances. The deepest measurements have revealed more microbial respiration, more organic matter burial, and more anthropogenic contamination than scientists ever expected. But at 10,135 meters, we still cannot map who eats what, when they eat it, or how. These profound ecosystems respond to change. Life exists at the bottom, but it abides by rules that surface biology barely recognizes. A world in motion, the dynamic geology of trenches. The seafloor at Hadal depths is anything but static. Trenches form at subduction zones, creating terminal sinks that trap sediment, organic carbon, and pollutants. But these are not passive collection points. They are dynamic systems where geology is in constant, violent motion. On March 11, 2011, the magnitude 9.0 Tohoku earthquake generated the most powerful seismic event in Japan's recorded history. Within minutes, massive underwater landslides triggered basin-scale turbidity currents that raced down the continental slope. The entire Hadal environment was transformed in real time. One ocean bottom pressure recorder actually captured its own displacement of nearly 1 kilometer across the seafloor. Not because it failed, but because the sediment beneath it liquefied and flowed downslope like an avalanche. These dynamics create operational nightmares. Thick nepheloid layers and fresh turbidity plumes can obliterate visibility for cameras. Active downslope flows corrupt acoustic ranging. Landers can be displaced by hundreds of meters or more. Accurate bathymetry becomes obsolete the moment the seafloor reshapes itself. In the Hadal world, earthquakes regularly push the reset button. Maps can become obsolete faster than our instruments can update them. The Explorer's Toolkit. Platforms for the abyss deep ocean exploration hinges on selecting the right platform for the mission. 4 distinct approaches dominate Hadal research. Today, human-occupied vehicles, HOVs. These place scientists directly at depth for real-time observation and sampling. The DSV limiting factor is the current state of the art. Their primary value lies in human judgment in complex terrain, but their time is precious and the costs are high. Remotely operated vehicles, ROVs. These offer real-time control through power and data tethers. They are excellent for precision manipulation at depths up to 6,500 meters, but full ocean depth tethering is brutally difficult and risky. Autonomous underwater vehicles, AUVs. These eliminate tethers by operating as programmable untethered robots, ideal for wide area mapping. Their flexibility, however, is limited by the slow and unreliable nature of acoustic communication. Landers. This is the simplest and most robust approach. Free-falling frames carry cameras and samplers to the seafloor, operate autonomously, and then drop ballast weights to return. They work reliably at full ocean depth, but each deployment provides data from only a single location. The winning strategy is a layered one, an AUV to find targets, an HOV or ROV to understand and sample those discoveries, and an array of landers to monitor patterns over extended periods. Each platform excels within its specific operational envelope, but none provides a universal solution to the challenges of Hadal exploration. Conclusion: the frontier remains. So why can't we fully explore the deepest parts of our ocean? Physics erects the first barrier, pressure. The second is the signal. Communication is agonizingly slow and unreliable. The third is the map. Most of the seafloor remains an uncharted void. Fourth are the staggering risks and costs. Fifth are the hurdles of politics and permits. Sixth is the ecology itself. Life there is fragile and alien. The ocean is not blocked by a single obstacle. It is gated by a formidable stack of them. Nearly 11 kilometers down, our list of unknowns is vast. We lack a comprehensive census of the deepest life. We do not fully understand the carbon cycle in the trenches. The seafloor itself moves and reshapes before our eyes. Even the simple number representing its depth fights back, shifting with our methods and the Earth's own movements. This is not a story of failure. It is the story of a frontier that answers our curiosity with pressure, silence, and distance. The rest is discipline. We must map more, design for silence, and hold to the simple, rigorous habits that make the deepest work possible. If mapping, just a quarter of the seafloor has already revealed lost mountains and forgotten shipwrecks, imagine what awaits in the remainder. The final 73% hides more trenches within trenches, more volcanic hotspots, more blind corners. Some days, the trench will still win. But on the next day, we will go back, with better maps, tighter links, and steadier hands.